morning. This is B. Naresh, working as an assistant professor in EC department. Today's topic is load line analysis, diffusion and transition capacitances. And coming to this load line analysis here, and why we are going to this load line analysis for a PN junction diode. So by using this load line analysis, we can examine the exact operating point. So from that operating point, we are calculating the AQ point here. So to observe this load line analysis, now the PN junction diode can be configured under the forward bias here. So what is the meaning of biasing here? So means that we need to apply an external DC source to an PN junction under the forward bias mode here. So based on this DC biasing here, then we need to observe the DC load line, and that should be intersecting on the characteristics of PN junction diode. And at which this DC load line is intersects the characteristics of a PN junction diode, that point is acts as a operating point or exact point here. So to observe this load line analysis in a PN junction diode, so here we are making the reactive components are made as 0 here. And from that, by using that voltage characteristics, now we are going to observe the load line analysis of PN junction diode here. So to observe this load line analysis of the PN junction diode, first we need to plot the VI characteristics of PN junction diode. So under this VI characteristics, actually we are having the two types of the characteristics. One is forward bias characteristics, another one is reverse bias characteristics. So from the characteristics, and we observe that, and a maximum current takes place across the forward biased PN junction diode, and there is no conduction takes place across the reverse biased PN junction diode here. So we need to use the forward biased PN junction diode here to observe the load line analysis here. And by using this load line analysis, we are going to examine the exact operating point for an PN junction diode. So coming to here, so here I am going to make the PN junction diode is forward bias here. So for this case, this is your PN junction diode symbolic representation, and this is the P-type material, and here this is N-type material. And for this P-type material, it is represented as anode, and here it is represented as your cathode here. Then we made an external DC source, and by using this external DC source, we need to make that PN junction, this PN junction diode is acts as a forward biased here. So how we are going to make this forward biased PN junction diode? So means from the DC source, the positive pole of the DC source is connected to anode of the PN junction diode, and the negative pole of this DC source is connected to cathode of the PN junction diode. Then it becomes your a PN junction diode under forward bias here. And due to this forward bias, a current flowing across this network, and that is represented as your a forward diode current is represented as your IR. Then here we are going to observe the output voltage across the load resistance here. Hence, I am going to place a load resistance across the diode. And from this load resistance, now we are going to calculate the output voltage, so across this load resistance here. So according to this configuration, and here this circuit now is acts as a forward biased PN junction diode. Under this forward biased diode, the current flowing across this network is represented as a diode forward current that is represented as your IF. And at this applied biasing voltage, the voltage drop across this diode is represented as your VF under forward bias mode. That is the reason it is represented as VF, where F indication is the which type of biasing we are using. So here we are using your forward bias mode here. So that is the reason here it is represented as the voltage drop across this diode is represented as VF under forward bias mode. And here this is the source resistance R, and the voltage drop across this resistance is represented as your VR here. And we know that in generally, so the diode offers a very small forward resistance here. So here we are neglecting this reactive component here. So now by using the circuit, now we are going to observe the how we are going to find out the load line here, then how to find out the exact operating point from the VI characteristics here. So we run the two methodologies here. So one is directly we plot the curve by using this Kirchhoff's current and voltage law, and other is directly we are plotting the volt ampere characteristics of the diode here. So for this case, now I'm going to consider this network, and here now I'm going to make the a load resistance RL, and across this RL now I'm going to find out the output voltage, and it should be made as a ground. And this circuit now here the PN junction diode is acts as under forward bias. Why? Because of that the positive pole of this battery is connected to a diode anode, and the negative pole of the battery is connected to diode cathode. From this point of view, we can say that this circuit is acts as a forward bias PN junction diode. So why we are considering only forward bias means the maximum current flowing across only the forward bias diode here. So that is the reason here we are considering the only the forward biased PN junction diode here. Now by applying the KVL, now we need to find out that one. So we need to draw a DC load line here. So how this DC load line is intersects the characteristics of the PN junction diode. And from that, so the intersecting point of this DC load line at the characteristics of the PN junction diode, and that point indicates the exact parameters of a PN junction diode under the forward bias diode. That is represented as exact diode forward bias voltage and exact diode forward current here. So for this case, for this network, I'm going to apply the KVL. So if you apply the KVL, what happens here? This is the source side. So Vin is equal to, here I'm neglecting this network resistance here. I made as this R, I'm assumed as a 0. Hence, this R is replaced with short circuit here. R is replaced with your short circuit here. So hence the Vin is equal to, so the voltage drop across this a forward bias diode voltage along with across this load resistance, the voltage drop is represented as your V0 here. So that is the reason it is represented as the Vin is equal to, and this is the VF. So this Vin is equal to, and the summation of the outgoing voltage sources here. So what is this voltage? So the voltage drop across this diode is VF, and the voltage drop across this load resistance is your RL. So, and that voltage drop across this RL is represented as your V0 here. So hence here it is represented as Vin is equal to VF plus V0. Now from the circuit, again we know that from the circuit, what is the output voltage? What is the V naught? And this output voltage we are going to measure across from this load resistance here. Under this network, which current is flowing here? The same current is flowing across this diode as well as your this load resistance here. So, and in this network, the diode is operated as your forward biased here. Hence, a forward current is flowing across this diode as well as your load resistance here. So from this circuit, here I am going to write. So what is the V naught? So V naught is equal to which current is flowing here? IF current, and across the resistance is your RL. Hence, from the circuit, the V naught is represented as. So from this circuit, this V naught at this point, we are going to calculate the output voltage across the load resistance, and at this load resistance, the diode forward current is flowing. Hence, the V naught is represented as IF into RL here. Now we can substitute this output voltage expression in this expression here. Now what happens here? So then the V in becomes, so then what is our first expression here? V in is equal to the summation of the diode forward voltage and the output voltage here. So here we observe that the output voltage is represented as IF into RL. Hence, this V in becomes VF plus IF into RL. Hence, here we are replacing this part. The V naught is represented as your IF into RL here. And from this, we need to observe means from the diode characteristics here. If you want to draw the diode forward bias characteristics, the x-axis is represented with your diode forward voltage, and the y-axis is represented with diode forward current here. Hence, from this expression, we need to observe how much diode forward voltage is generated here. Hence, we need to calculate this VF voltage from this expression here. So, from this relation, what is the VF here? So, to write this here from this equation, the VF is equal to V in minus, this term is taken outside here. So, what happens here? This is VF is equal to V in minus IF into RL here. VF is equal to V in minus IF into RL. So by using this expression, now we are going to identify the 2 points, and those by using those 2 points, now we are going to draw a load line. That load line is called as the DC load line here. So hence, so by using this circuit, again here I need to draw the load resistance here, and here it is represented as RL, and this is V naught here. So we observe this relation. Which relation we observed here? The diode forward voltage is represented as V in minus IF into RL. To define the quadratic points here, first I am going to substitute this V in is equal to 0. If you are going to substitute this V in is equal to 0 at this point, what happens here when V in is a 0? What happens then? So I taken this relation, VF is equal to V in minus IF into RL. So here I made this V in is equal to 0, means VF that is equal to 0 minus IF into RL here. Now from this, I need to calculate how much diode current is flows. So at this point, IF is represented as VF by RL, and the polarity is negative sign, means this is not a negative current. It indicates that the direction of flow of current here. So from this relation, we observe this when the V in is 0, it allows the maximum current, under the forward bias, that is represented as IF is represented, it is a ratio of out diode forward voltage to the load resistance here, RLA. Similarly, if I made this IF is a 0, the same equation, suppose I consider the same relation. The relation is VF is equal to Vin minus IF into RL. In a second case, what I substitute here, I am substituting this diode forward current is a 0, hence what happens, this VF is equal to Vin minus 0 into RL here. So this 0 into RL becomes your 0, hence the diode forward voltage is exactly equals to your Vin here. So by using these two quadratic points, now we are going to observe how we are going to draw the DC load line by using the diode forward characteristics here. So to identify the exact operating point, or the exact operating point means that operating point contains the two parameters. One is a voltage parameter, another one is a current parameter here. To observe this exact operating point, by using these two coordinating points, we are going to draw a straight or a load line, and that load line is called as here the DC load line here. So for this case, first here I am going to consider the characteristics of PN junction diode under the forward bias here. So let us take, so and this is actually y-axis, I consider the current. So means this is the maximum current, that is IF, and this x-axis we are representing the diode forward voltage here. And let us take this is a 0, and this is a diode forward bias characteristics, and where that AB, this point and this AB line here, it is called as the DC load line here. But how we need to draw this DC load line here? For this case, let us assume that in the first case, when Vin is a 0, so where these are the 2 points, when we substituted this Vin is a 0, we observed that the maximum current is a ratio of Vf to the RL here. So at this point, this current is represented as your maximum current. So that is the reason. Here, so this point I'm intersecting when Vin is a 0. At this node, it contains the maximum forward current. IF is represented as Vf by R here. So this node here, it is represented as IF, that is equal to Vf by RL or R, no problem. And similarly, we also observe that when IF is a 0, in the second case, we observe that when IF is a 0, we observe Vf is equal to your Vin. So hence, when IF is a 0, the diode voltage under the forward bias, that is exactly equal to your applied input voltage here. So hence, this node, this A point is indicates that when the diode current is a 0, and we observe this, the diode forward voltage is equal to your Vin voltage. After locating these 2 points, then we need to join these 2 points. After locating these 2 points, now we can join these 2 points A and B. We can join this A and B, line, and that line acts as your load line here. That line acts as your load line. And this line here, it is called as a DC load line here. And this DC load line intersects the characteristics of this PN. So at this point, This point is acts as a intersecting point in a characteristics of PN junction diode. And this node indicates that a exact operating point, and this operating point contains the two parameters. One is voltage parameter, another one is your current parameter here. And this slope is nothing acts as the straight line is acts as a DC load line here. So how we are going to show that how this DC load line is a slope here? So for this case, so yeah, this exact operating point is also called as the Q point here. Means what is the Q point here? So where the DC load line is intersects the characteristic curve of PN junction diode under the forward bias, and that point is called as your a Q point or a operating point, or it is also called as the exact point here. So now we need to observe this slope. So how we are going to make this one? Then from the mathematically, I'm going to show that then what is the slope of this DC load line. So for this case, we have this equation. What is the, we already observed this one. The diode forward voltage Vf is represented as Vin minus If into RL. If you are rearranging this equation, so if I rearranging this equation means I taken this term is outside. So means IF RL that is equal to Vf minus your Vin here. So from this, so just you can take this Vin is outside. So what happens here? Vf minus Vin that is equal to minus If into your RL. The same equation I represented here. So from this, I'm going to observe the diode current here. So means I taken this RL to the side. IF is equal to this minus RL minus 1 by RL times of VF, minus of minus becomes your plus Vin by RL here. So for this case, mathematically we know that the slope expression Y is represented as mx plus c. So here where m is represented as minus 1 by RL and c is constant, that is Vin and RL here. And here the reciprocal of this resistance, actually in a linearly the resistance is represented as a linear curve. But the reciprocal of this resistance, and that is nothing but your a DC load line. Where what is the M parameter? This is the reciprocal of your load resistance 1 by RL. And that line here it is called as the slope of that load resistance ends, and that slope of the load resistance here it is called as the load line here. So up to this point, now we observe that what is the load line analysis of a PN junction diode, and what is the need of this load line analysis of PN junction diode. And next coming to you, a diode capacitances here. So how the diode here it is acts as a capacitance here. Generally, we know that the capacitance means it contains two parallel conducting plates. In between those two parallel conducting plates, a dielectric media is there. So those two plates can act as it to store some charge here. So now we are going to show that how this diode is also exhibits the capacitances here. And based on the biasing concepts of PN junction diode, here this diode exhibits the two types of the capacitances here. One is a diffusion or a storage capacitance. Another one is transition or a depletion region capacitance here. One is diffusion or a storage capacitance. Another one is transition or depletion region capacitance here. So here, once this storage capacitance is absorbed from the forward bias characteristics here of PN diode or a PN junction diode. This transition or depletion region capacitance is absorbed from the reverse bias characteristics of PN diode here. So before going to this to identify the diffusion or a transition capacitance, first we need to observe how this PN junction diode acts as a two conducting plates, and in between how it exists the a dielectric media or insulator between the two conducting plates here. So for this case, so first I observe that. So let us consider this is a normal PN junction diode with unbiased or a zero bias. What is the meaning of this unbiased here? Means there is no external force is applied to an PN junction diode, and that PN junction diode is acts as your unbiased diode. So what happens in the unbiased diode? And let us take, and one off is the doped with a trivalent impurities, then it is acts as a p-type extrinsic semiconductor. Similarly here, another off is doped with pentavalent impurities, then it is acts as your n-type extrinsic semiconductor. And we know that in a n-type, these are the majority charge carriers, those are represented as electrons. So these are the electrons here. And a minority charge carriers are represented as holes. This white color representation is holes, and this orange color indication is for electrons. Similarly, based on the doping levels in this semiconductor side, and here the majority charge carriers are holes and a minority charge carriers are electrons. Even though if you are not applying any external force to this PN junction due to the internal energy of a charge particle, they are trying to move or diffuse from the one region to the another region at, and they're trying to diffuse from one region to the another region. Under this condition, at a certain point, it loses its energy, then it becomes the immobile ion here. And this nearby junction for the P side, this majority charge carriers becomes the immobile ion, that is represented as a negative ion. And whenever the electrons are trying to diffusing from the n type to p type, whenever it loses its energy, it becomes that immobile ion, that is represented as your positive ion. Hence, it creates a space charge region. This is called as the depletion width, or a potential barrier or a space charge region is established nearby the junction due to the movement of diffusing the charge carriers from the one region to the another region with unbiased condition. Now we'll see what happens when we apply the biasing condition to and this PN junction here. If you are applying the forward bias, so means I'm showing this is a forward bias condition here. So means the P type is connected to positive pole of the battery, and N type is connected to negative pole of the battery, and this type of the biasing becomes your a forward bias here. Under this forward bias, what happens here? We are applying some external force or extra force to that charge particular. Due to that extra force, the charge carriers are trying to diffusing from the one region to another region to break this structure, this diffusion region. Compared with this unbiased to forward bias diode, under this forward bias, what happens here? It reduces the depletion width. Then what happens whenever it reduces the depletion width? So more amount of the charge carriers are diffusing from the one region to the another region to form the electron and a hole pair. And whenever this electron and a hole pair disappears, a conduction takes place across the junction. So hence it allows the maximum conduction. From this point of view, whenever it stores some amount of energy here, it acts as a one conducting plate. So here this P side, this plate is acts as a conducting plate, and here this side is acts as a one conducting plate. Between a one depletion width is there, that is acts as a dielectric media here. And similarly, we need to observe the same how what happens if you are using the reverse bias condition here. So for this case, and this is the unbiased condition, if you are applying the reverse bias to an unbiased p-n junction diode, now we'll see what. So what is the reverse bias diode? The p-type electrode means p side is connected to negative pole of the battery and n side is connected to positive pole of the battery. Under this condition, so here the majority charge carriers are not diffusing from the one region to another region, but the majority charge carriers of P type and N type are attracting towards the battery. So hence here the holes are diffusing towards battery. Here the electrons are diffusing towards the battery. That is the reason. Whenever the charge carriers are leaving this place, it creates a one empty space, and that is the reason it increases the depletion width under this reverse biased condition here. So here also, here this P type and N type, here it is acts as a two conducting plates between. So if the depletion width is increases means there is no movement of the charge carriers. The majority charge carriers from the P side to N side or N side to P side. Hence there is no recombination of electron and a hole pair. That is the reason it does not allow the flow of conduction across the p-n junction under this reverse biased p-n junction diode. So by using this principle, now we are going to observe the capacitances here. There are the two types of the capacitances here. One is diffusion capacitance, another one is your transition capacitance here. The diffusion capacitance is absorbed from the forward biased p-n junction diode. So hence, I use this forward biased p-n junction diode. And in this case, let us take the movement of minority charge carriers. The movement of minority charge carriers are diffusing from the one region to the another region. Before it crossing from the one region to the another region, the minority charge carriers are establishes the charge nearby the junction, and that charge is stored on this plate. So that is the reason. And before it recombines with another region, and those minority charge carriers generate the space nearby the junction, and that amount of voltage, the rate of change of that amount of voltage with respect to your applied energy. From that, we can calculate the diffusion capacitance of p-n junction diode. So that is the reason here I mentioned this point. The diffusion capacitance, of course, due to the stored charge of minority electrons and the minority holes, means these are the minority charge carriers. So if you consider the p-type, the minority charge carriers are electrons, and if you consider the n side, the minority charge carriers are holes. So with respect to your applied energy, these minority charge carriers are diffusing from the one region to another region. Before it reaches to the majority charge carriers, it creates some charge, or it establishes the charge nearby this junction, and that from that point it is acts as a conducting plate here. So that is the reason a large number of charge carriers are trying to move from the one region to the another region will be accumulated nearby this region before the recombine with the majority charge carriers. So before the recombine with the majority charge carriers, it establishes the a charge across the or nearby the junction, and that voltage we are going to measure as a diffusion capacitance here. So for this case, from this analysis, the diffusion capacitance is defined as the rate of change of charge for an either electron or hole with respect to the rate of change of applied voltage here. So from that, I represented as where this CD is represented as diffusion capacitance, and the dq is the change in number of minority charge carriers are stored outside the depletion region. So due to this effect of the storage of minority charge carriers outside the depletion region, means outside the depletion region means it acts as some energy source. So means it stores some amount of energy before it recombine with the majority charge carriers here. And dv is how much charge we are going to apply. So if the biasing energy the changes, the rate of change of minority charge carriers is also changes here. So from that point, we are observing the diffusion capacitance of PN junction diode under the forward bias condition. Similarly, another capacitance, that is a transition capacitance, and here this transition capacitance is absorbed from the reverse bias characteristics of PN junction diode. So that is the reason. First, I consider this PN junction diode under the reverse bias mode. So this is the P side, and here this electrode is represented as anode, and here this electrode is represented as your cathode. Here the anode is made with the negative pole of the battery, and the cathode is connected with the positive pole of the battery. Hence, the PN junction diode acts as your reverse bias. So here we observe that due to this applied external force, the majority charge carriers are attracting towards the battery. Hence, it increases the depletion space charge region or a potential barrier width here. So why? Because of that, these are the charge carriers are not diffusing towards the internal region. These are the diffusing towards the battery side. Hence, the more number of positive and negative ions are established across the junction. So that is the reason. And it acts as a this one whenever it stores some amount of energy, and that is acts as your plate, conducting plate, and then inside another conducting plate. In between, we are having some insulating media. So hence, from this reverse biased PN junction diode, we are going to observe that how much capacitance is occur, and that capacitance is represented by transition capacitance. From this analysis, so, and here I'm saying that what is this depletion region contains. So we know that the depletion region contains immobile ions. So nearby the P side, that is the negative immobile ions, and nearby the N side, the immobile ions are positive ions here. So hence, so this region, this P type and N type is acts as a conductor or electrodes, and this media is acts as a dielectric media for these two conducting plates. From that principle, it acts as a capacitor principle. Hence, we are measuring this capacitance, how much capacitance is occurred under this reverse biased PN junction diode. That is represented as a transition capacitance. It is represented as your CT here. So from this, the transition capacitance is mathematically is represented as epsilon A by W here. So where the CT is transition capacitance and epsilon is permittivity of the semiconductor, that is represented as epsilon naught and epsilon naught, where epsilon naught is permittivity in a free space, that is represented as 8.849 into 10 to the power of minus 12. Similarly, epsilon r is represented as relative permittivity, that is a 16 for germanium and a 12 for silica, and where A is the area of the plates of P type and N type regions, and W is the width of the depletion region here. So means this is your this is the depletion region. Width here it is represented as W, and here A means this is the area of the P type and your N type here. So from that we are representing this. A transition capacitance is represented as epsilon A by W here. So up to this point, today we observed that the load line analysis of the PN junction diode as well as the two diode capacitances here, that is storage capacitance or diffusion capacitance and transition capacitance here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.